The Fall Academy is back, and today I want to talk about the Zeeman Effect. So, essentially, what we've learned before, or might have already learned this, is that to solve for the Schrodinger equation for the hydrogen atom, you essentially write the Laplacian in spherical coordinates, and you write that, and you know that the wave function is a function of r, theta, and phi. And using separation of variables, you can separate the r dependence and theta dependence and phi dependence because there's no cross terms in any of those in the wave function in the potential operator. So, which means if I separate r, theta, and phi and using boundary conditions, I get that the quantum number L, which stands for the angular momentum, total angular, just the it's the angular momentum quantum number, and it's from 0 to n, where n is the principal quantum number, which dictates what the energy of the system would be given here, and m is the z component of angular momentum. So we know that from classical physics, the dipole moment is proportional to the current times the area. And in classical physics, if you have an electron going around a proton, then uh, then the current would just be equal to QV times 2 pi r, where 2 pi r is the circumference, times the area, which is pi r squared. So you get this QVR term. And you know that V and R are orthogonal, or they're perpendicular to each other, which means that I can write, which means which means I can write VR in terms of the angular momentum L, which is just a cross product of R and P. And doing that, doing that sub I get that the magnetic moment is minus E times the angular momentum operator over 2me, and that the potential is equal to m, the magnetic moment to m. Uh, and then given that the potential is proportional, which is always the case, minus times the magnetic moment times the magnetic field, then I can write potential in terms of the angular momentum. And in this case, since I've drawn in this picture that the magnetic field is in the positive z direction, which means the I can write the potential in terms of the z component of angular momentum. And given that that's the case, that means the correction I make to my Hamiltonian is the original Hamiltonians that I had, which was this, plus this term, this new potential term that I have, that's proportional to the magnetic field that's being exerted on to the electron. And given that I know that the m quantum number is an eigenvalue to this z component of angular momentum operator, that means I can write the corresponding wave function using the time independent wave function, where to solve for which time independent Schrodinger equation, which has a definite energy state in terms of the energy E sub n, which I've described here, plus this new plus plus this term, which comes from the potential due to the magnetic field. And given that, I get that the new energy is proportional to the energy sub n, which just depends on the principal quantum number, plus this plus m, where times b times the Bohr magneton, which is just equal to EH bar 2me, which is just to make units more convenient. And once we do this, since the energy now depends on m, there's no more degeneracy in the m states when you transition states. Different m values correspond now to different energy states. So given that, that means if we pass an atom onto a magnetic field B, if what we see in the detector is that depending on what the m value is, it'll get deflected in different ways because the m values now don't correspond to the same energy states anymore.